A huge part of my state machine for procedural animation is two words: collision detection. There are quite a few ways that you can detect the environment in Unity, but today I'm going to show you how I did it in my state machine and go through every detail so that you can do it too. It's been a while since I've dropped a new video around here, so for those who are new, my name is Nikki, welcome to iHeartGameDev. Let's get started. Our environment interaction procedural animation is going to work by detecting objects that are close to our character. There are technically many ways that this can be done, but for our implementation, we're going to use a single collider that remains in front of our character at all times. While we can manually add a collider and adjust its size, there's actually a way that we can programmatically create a collider for our procedural animation purposes. In the environment interaction state machine class, create a new method titled Construct Environment Detection Collider. For our project, the collider's width should equate to roughly the wingspan of our character, because that is the furthest the character's arms will be able to reach. Let's create a new float variable titled Wingspan. A character's wingspan is typically very close to their height. This means we can set the wingspan variable equal to the root collider's height property. It's worth noting that this method does assume that the root collider is set up correctly to match the character's height. Using the add component method, pass the box collider type specifying the type of component we want added to the environment interaction state machine. Then set the collider's size property equal to a new vector 3, passing in the wingspan variable for x, y, and z. The collider will now be set to what I determined to be an appropriate size for detecting the environment. Placement of this environment interaction collider is also important. If we invoke this new method in Awake and test in play mode, we'll see it default to a 0x, 0y, 0z local position. However, using the wingspan again, we can find the correct placement. Set the collider's center position equal to another new vector 3, passing in the root collider's center x position for the x value, the root collider's center y position plus a quarter of the wingspan for the y value, and the root collider's center z position plus half of the wingspan for the z value. Using the root collider's x value means that it's centered with our character. Using the y value plus the additional 25% of the wingspan will elevate the box collider roughly an arm's height off the ground, and setting the z value to 50% of the wingspan will push the collider forward so that the entire collider is directly in front of the character. The last property to update before the collider is complete is the isTrigger property. Setting this value to true will remove physical collisions, and instead have the collider trigger events when interacting with other colliders in the scene. We'll use this to detect when our character is close to interactable objects and update our procedural animation. And remember, our base state declared abstract onTrigger events. This trigger will now call each. Testing in play mode, and we can now see that the collider is created on the environment interaction rig game object. The collider is positioned directly in front of the character, and it's able to pass through other objects because it's a trigger. Perfect! Now, if you're not getting the same results as we are here, maybe due to abnormal proportions of your character, go ahead and remove the code and manually add a trigger collider to the environment interaction rig instead. With the initial setup of the state machine complete, how will the environment interaction actually work? In the environment interaction state machine, when the character gets close to an object, the trigger collider placed in front of the character detects the collision with the object. By utilizing trigger events and other built-in methods in Unity, we can determine the closest position on the object's mesh where the collision occurs. As the trigger continues to intersect with the object's collider, we can continuously update this closest position. Simultaneously, we adjust the position of the inverse kinematics target in each environment interaction state, based on the distance between the character and the object. When the trigger exits the collider, we remove the closest position data and reset the IK target to its default position. Let's focus on how we can calculate the position from the character to the collider. Each state in our state machine implements the onTriggerEnter, onTriggerStay, and onTriggerExit methods. And our State Manager Abstract class calls these monobehavior-based methods with the current state. OnTriggerEnter is called when the trigger first intersects with the new collider. OnTrigger state is called as long as it continues to intersect with the same collider, and OnTrigger exit is called when they no longer intersect. These methods all provide access to the collider that the trigger intersects with. In our abstract environment interaction state class, we'll create a new method, getClosestPointOnCollider. It will return a vector3 and expect a collider, intersecting collider, and a vector3 position to check. Colliders in Unity expose the method closestPoint. getClosestPointOnCollider returns the value of intersecting collider calling closestPoint and passing in the position to check. Okay, we have a method that returns the closest point on the collider, but what is it closest to? What should we pass as the position to check argument, and where should we actually use this method? We will invoke it in a couple of places, and you'll see why in a moment. The environment interaction state machine consists of 5 states. Some of them perform the exact same logic in the onTrigger callback methods, but some of them don't. For example, the reset state won't have any logic in onTrigger enter, stay, or exit, because the state's purpose is to reset the state machine. Meanwhile, the approach and rise state may both require the use of getClosestPointOnCollider as we track and update the IK target position where we want our character's hands to move. One of the most famous principles of programming is to keep your code dry, aka don't repeat yourself. While we can't have the environment interaction state define logic for all of the states in the onTrigger enter, stay, and exit methods, because as we just explained, those might be different depending on the state, we can instead expose new methods in this abstract state that the concrete states can inherit and choose to invoke in onTrigger callbacks. Let's add 3 new methods to the environment interaction state. Start IK target position tracking, update IK target position, and reset IK target position tracking, all of which expect an argument intersecting collider of type collider. We can use these methods to call getClosestPointOnCollider, and this allows states to individually decide if they want to use each method. Getting back into the weeds of our procedural animation, an important step for our machine is to evaluate which side of the character is closer to the target, the right or the left. This is important because it dictates which 2-bone IK, multi-rotation constraint, and IK target values are updated by each state throughout the animation. Fortunately, we can reuse our getClosestPointOnCollider method to help find which side to use. In the context file, we'll create 5 new variables: current IK constraint of type 2-bone IK constraint, current multi-rotation constraint of type multi-rotation constraint, current IK target transform, current shoulder transform, both of type transform, and current body side of type eBody side. All of these variables are public but have private setters. Now let's define eBody side. eBody side is a public enum nested within the environment interaction context with right and left values. We've added all of these variables. Now to set them in a new method, SetCurrentSide. This method takes a vector3 parameter named position to check. By utilizing the stored left and right 2-bone IK constraint in the context, we can determine the side that is closer. Using the vector3.distance method, we can compare the distance between the position to check and both of the character's right and left shoulders, determining which is closer. In the case that the left is closer, we set the current body side, current IK constraint, and current multi-rotation constraint to the eBodyside.left enum, left IK constraint, and left multi-rotation constraint values, respectively. And if the right is closer, we'll do the same for that side's values. Outside of the if conditional, we can set the current shoulder transform and current IK target transform values to the current IK constraints root and target transforms. At this point, those are correctly set to the right or left side. Now, in our environment interaction state, we can use SetCurrentSide to determine which side should perform the procedural animation. We'll want to do this at the start of the procedural animation flow, aka when our constructed trigger collider first intersects with another collider. Let's establish here that start IK target position tracking is the method that we can expect to pass to the onTrigger enter methods of each state that should use it. And with that agreement in place, we should use SetCurrentSide in this method. Context.setCurrentSide is passed a vector3 closest point from root. That is set to the return result of getClosestPointOnCollider. This method is called with the character's root transform position and the intersecting collider that startIKTargetPositionTracking receives as an argument. We'll need to add the root transform as a variable in the context, and add it as an argument when the context is instantiated. Then create a public getter so that it's accessible throughout our state machine. And of course, actually pass the transform root in the instantiation. Now, whenever startIKTargetPositionTracking is called, we expect the current side and associated variables to correctly update. Let's try placing a log in the left and right side conditional blocks to test out our method and see if it works. Our reset state is not going to use any of the on-trigger callbacks, but the search state will. For now, let's have the reset state immediately return the search enum. This causes our state machine to immediately switch to the search state the first time update state is run. And now we can call startIKTargetPositionTracking in the onTriggerEnter method of the search state. Entering play mode, we can now see that as the character approaches the colliders in the environment, the right and left side are correctly being logged. However, when our character is moving in a dense environment, chances are that the trigger will intersect with many colliders. Ideally, we filter for objects we want to interact with using a layer like Interactable. In the startIKTargetPositionTracking method, we'll wrap our logic in a new if statement. The intersecting collider provides access directly to its layer through its game object. Using Unity's layer mask and its built-in nameToLayer method, we can ensure that our logic will only be run if the game object has its layer set to Interactable. Now, we just need to create and set this layer name for the game object that we want. In play mode, we'll now see only the interactable layer will be logged. But as the character moves around, it's also possible there are multiple objects with this layer. This would restart our procedural animation cycle over and over again. To fix this, add another public variable in the context titled currentIntersectingCollider of type collider. Then, add a check that currentIntersectingCollider is equal to null after the layer validation. Now we just need to set the currentIntersectingCollider at the top of startIKTargetPositionTracking method. This ensures that once the procedural animation starts, it won't transfer to another collider. And to reset this value, let's implement resetIKTargetPositionTracking. Validating that the exiting collider argument is equal to the current intersecting collider, we can set the current intersecting collider back to null. Let's try testing our implementation again by adding the call to resetIKTargetPositionTracking in the onTriggerExit method of the search state. In our Unity scene, first create the interactable layer. Then we can add a few game objects and mark them with this layer. Entering play mode, and now, as the character moves around the environment and the trigger collider enters and exits the interactable colliders, we can see the logs showing up in the console. Okay, we are able to accurately determine the correct side for our character's procedural animation. Now we want to calculate the closest point on the stored collider from that side's shoulder. Using the shoulder gives us a reliable and natural result when we reposition our IK target. In the environment interaction state, let's create a new method, setIKTargetPosition. This method will start by setting a new variable, closest point on collider from shoulder, which we'll store in the context with a default value of vector3.positiveInfinity. This variable will be equal to the return value of getClosestPointOnCollider, passing in the context currentIntersectingCollider. Now we could just pass in the current shoulder transform position that's stored in the context as the second argument, because we know that's the current side's shoulder position. However, let's use Unity's built-in debugging gizmos to visualize the problem with this vector3. To showcase the problem, call setIKTargetPosition at the bottom of startIKTargetPositionTracking method, and in a similar if statement for the updateIKTargetPosition method, validating the intersecting collider argument is the same as the stored collider. Be sure the search state now calls startIKTargetPositionTracking, updateIKTargetPosition, and resetIKTargetPositionTracking in the respective on-trigger callbacks. Then, in the environment interaction state machine, let's add the onDrawGizmoSelected method. Inside this method, set the gizmo's color to red and add a conditional statement. If the context exists and the closest point on collider from shoulder variable is not equal to null, then have the gizmos draw a sphere at that position with a small 0.03 radius. Testing in play mode and moving to an interactable surface, we can now see the closest point from the shoulder position is rendering from the gizmo. Awesome. However, there is a problem: the y-axis. As our character moves, the shoulder height is not always the same. This can lead to issues down the line when we determine if the character is getting further away from the interactable surface and we're trying to understand if we should reset the animation. To prevent this from becoming a problem, let's store the shoulder height separately one time. An easy place to do this is in the context constructor. Here we can set a new variable, character shoulder height, and we can set it to either the left or the right root bone's y position. In our setIkTargetPosition method, instead of passing in the current IK constraint's root bone position, we'll use a new vector3 which extracts the x and z positions from the current IK constraint's root, but uses our new character shoulder height variable from the context as the y value. Entering play mode, and we can now see that the y position at the closest point is consistently at the same height. Nice. But what happens when we exit the collider? We need to reset the closest position. In the resetIkTargetPosition tracking method, we'll set the closest point on collider from shoulder variable back to positive infinity. Now that we have the closest point on the collider from the character shoulder, we can start to calculate the placement for the IK target of the current two-bone IK that's in use. You may think that we can just set the current IK target transform equal to the stored closest point. However, doing this clips the character's hand right through the interactable surface. What we need to do is add an offset to bring the hand closer to the character. Let's start with the direction. In the setIkTargetPosition method, create a new vector3 ray direction and set it equal to the current shoulder transform's position minus the closest point on collider from shoulder. This provides us with a new directional vector that points from the stored closest point in the direction of the character's shoulder. We'll normalize this value to create a unit vector pointing in the correct direction. Next, we'll create a float titled offset distance and set it equal to 0.05. The offset will be equal to the normalized ray direction times the offset distance. And finally, a new vector3 offset position. This will be set to closest point on collider from shoulder plus this offset value. To piece it all together, set the position property of the current IK target transform, which we know as the red blocks in the editor, to this variable. We'll come back to this final assignment later on as we explore each state, but for now, we can test our current implementation in play mode. As the character approaches the wall, the current IK target snaps to the closest point. But nothing else happens. A core piece of any rig are the constraints weights. Thus far, we haven't made any changes to the weight in our code, but programmatically updating the weight is an important part of the environment interaction state machine. To showcase the work that we have done, here's what happens when we have the weight set to 100 by default from the inspector. The IK constraint clearly overrides the movement of our character's arms. But as we approach the wall, we can see the current IK target snap to the point on the wall. So far, so good. Our next step is to shift focus to each concrete state's implementation and get our procedural animation to look a little more natural. Next time, we'll program the transitions between each state and make the procedural animations even more realistic. If you love state machines just as much as I do, be sure to subscribe because it's a topic I cover frequently here on iHeartGameDev. If you'd like access to this project's files, be sure to check out the channel Patreon, where you can get the completed project while supporting the channel. Thank you to all of the current patrons for the continued support of the channel, and a special shout out to TerrorDev, Jupe, Angelo Tolaro, Peter Steiner, and Tendinitis for the top tier support. Hop into the channel Discord if you'd like to join an awesome growing community of developers just like yourself. But that's all for today. Thank you so much for watching, and I'll see you in the next video.